All right, let's take a look at exercise 1, all the parts. So first part A, we got the limit as x approaches 6 of 1 over x minus 6. Now I'm looking at this, trying to find the limit of the top, limit of the bottom separately. First, the limit of the top is 1, right? Limit of the bottom, if we just looked at limit of x minus 6 as x approaches 6, we could DSP just the limit of the bottom and get 0. When the limit of the top is non-zero, limit of the bottom is 0. This is the time to make a chart of x and y values, right? So we'll look at this. We'll actually do 2 charts, right? So we'll look at like approaching, x approaching 6 from the right. And the whole point is there's x values and there's y values. You know, then x approaching 6 from the left, so 5.9, 5.99. And approaching 6 from the right, so 6.1, we'll have 1 over 0.1, which is 1 over a tenth, in other words, the number 10. Here we'll get the number 100, similarly. We plug in 5.9 for x, then the y value, 1 over 5.9 minus 6, is 1 over negative 0.1. So that'll be negative 10, and this will be negative 100. The point is that the limit of this function, if f of x, we just mean this, x approaches 6 from the right, this will be a plus infinity, which will not equal the limit of this function as x approaches 6 from the left, right? This is a negative infinity, this is a positive infinity, therefore this limit here does not exist. Okay, part B, we'll take a limit, look at limit as x approaches 6 of 1 over absolute value of x minus 6. Now, look, still limit of a fraction. Just like before, we take limit of the top, limit of the bottom separately, just to see what's going on. The limit of the top is a 0. The limit of the top is a non-zero, is 1. The limit of the bottom is 0. We won't write 1 over 0, right? But just knowing the limits of the top and bottom tells us again to create a chart. The chart's going to look very similar. So we'll have here x value is just slightly bigger than 6, so like 6.1, 6.01. Y value, same data as over here, 10, 100. The difference now is when we look at the limit on the left, so we use x values like 5.9, 5.99. Then here where we had a minus, the absolute value is going to take care of that. We're going to get y value of 10 and y value of 100. So look, both the limit of this function as x approaches 6 from the right, and the limit of this function as x approaches 6 from the left, both of these are now going to be a plus infinity. Because these match, then this is also going to be a plus infinity. So sorry that the question's up there, the reasoning is here, and I went back over there. But because you've got the sheet, I hope it's kind of clear enough where the question is and how we're doing the answer. Look, for both of these limit problems, I think the key thing to think about is there are x values and there are y values, and plural on both. There's x values, and we could have even done more in this table, right? So x values, plural, y values, plural. If you try to look at a limit problem, you only look at x approaches 6, but you don't look at this part at all, you won't get to the limit problem. Right? So make sure to look at how this, what function you're taking the limit of. Let's try a couple other things then. For part C, that was the limit as x approaches 6 of x squared minus 36 all over x minus 6. If you compute the limit of the top and the limit of the bottom separately, you're going to get a 0 for the limit of the top and a 0 for the limit of the bottom. Please do not write equals 0 over 0. Don't write that, okay? But because the limit of the top, limit of the bottom are both 0, what we can do is, a little bit of algebra. So we'll still write the limit part because we're not ready to deal with the limit yet. But we can factor the top, x plus 6, x minus 6. Leave the bottom and x minus 6. Cancel the same factor on top and bottom. So we're left with limit as x approaches 6 of just the x plus 6 that's there. Now we have limit of a polynomial. Here we can apply DSP. By the way, if you had x approaches infinity, you can't apply DSP because DSP is about actually plugging in, and infinity isn't a number. Okay, so here we'll plug in, so no limit written. We'll have 6 plus 6. In other words, we'll have the number 12. That's one way to do this problem. But we're going to actually look at part C a different way. now that we're towards the end of the semester, there's actually another way to look at this problem. Because look, as we said earlier, limit of the top is 0, limit of the bottom is 0. Now, we won't write equals 0 over 0 here. No, that would not be correct to write. But we can write 0 over 0 on top of that equal sign to just indicate that this is a L'Hopital problem. So L'Hopital says we can now turn this limit problem into a new limit problem. And what we're going to do is, because what L'Hopital's rule requests, is we're going to do two derivatives. We're going to differentiate the top, and we're going to differentiate the bottom separately. And that's because that's what L'Hopital's rule asks for. L'Hopital's rule never asks us to differentiate the fraction as a whole. So when we differentiate the top, we differentiate x squared minus 36, we'll get 2x. We differentiate the bottom, that differentiates to 1, 6 differentiates to 0, we just get that. Okay, in other words, we have limit x approaches 6 of, just not writing the over 1, and this is a polynomial, so here we can also apply DSP. So plugging in, so no writing limit now, we just plug in a 6 here, so 2 times 6, we get the number 12. We get the same answer in a fundamentally different way, right? But now that we're at the end of the semester, we can do like, there's a L'Hopital's way to do this, and the traditional, if you see a 0 on top and a limit of 0 on bottom, we use to factor and cancel common factors. Okay, let's try another one. Part D. Limit x approaches 6 of x squared minus 36 over x plus 6. Okay. Well, look, when we compute the limit of the top, it's 0. When we compute the limit of the bottom, we get non-zero. Right, this is actually a rational function, and 6, that number here, is in the domain, right? So we don't end up dividing by 0. So we can use the direct substitution property for rational functions and just plug in, no writing limit here. Okay, if you do, look at how the DSP looks. There's no limit on the right side of that formula. And then this is 0 over 12, which is going to simplify to 0. Another way to do this, just to point this out, right, we can also say, let's take this problem, and look, the key thing is the limit of the bottom. Let's just put our justification here. The limit of the bottom was, well, due to DSP here, is the number 12. Because the limit of the bottom is a number that is not 0, we can apply the quotient law of limits. That is, we can split the limit to the top and the bottom separately. It's just a different way to do the problem. Like that, right? And then the point is the limit, so there's two new limit problems here. Sorry for this work getting in the way. But we have, so this limit problem here, let me just circle this in another color. Right? So this limit problem right here, we can put the result of that there. And this other limit problem right here, we can simplify that off to the side and write the result of what that is here. Now what's in blue, we actually already did. This limit problem right here, we just did it, right? This simplified to 12, so let's just copy that work. Then finally, just stare at what's in red. Right? Limit x approaches 6 of x squared minus 36. So we've zoomed in that far, so we don't see the fraction bar. We've zoomed in far enough to see the limit of a polynomial. We apply DSP there, and there's 6 squared minus 36. So we end up with 0 over 12 again, which simplifies to 0. So two ways to do it. It's either DSP for a rational function, or we can split the one limit of the fraction into the fraction of two separate limits, because the limit of the bottom is a number that is not 0. Okay, that's part D. Let's take a look at part E. Limit x approaches 6 of x squared plus 36 over x plus 6. Well, same deal, just like we did over there. Look, because this is a rational function and 6 is in the domain, we can just plug in 6 and have 6 squared plus 36 all over 6 plus 6. Right? So, you know, whatever number, I think 72 over 12, however that simplifies. Not really worried about it here. Another way to do this is we can, you know, same principle as we saw over here. Because the limit of the bottom is non-zero, just like over here, right? The limit of the bottom was 12. Same bottom right there, right? We can split this. We can limit. The only time you can split like this Sorry, just took some time to copy the problem. The only time you can split like this is if the limit of the bottom is non-zero. If the limit of the bottom is 0 and you split like this, you're using that limit law number 5, I believe it is, in a time when it doesn't apply. So please be careful there. Okay, same deal here. The top, just what's on top, just like what was circled red there, just what's on top, we can apply DSP, because what's on top of the fraction bar, above the fraction bar, is a limit of a polynomial, right? So we'll have 6 squared plus 36. Limit of what's on bottom, 6 plus 6. DSP there as well. Let's take a look at part F. Part F. Ooh, yeah. Okay, so now we're in sine of x over x cubed. This smells like squeeze theorem, doesn't it? So sine of x is between -1 and 1. If we divide all 3 sides of this inequality by x cubed, we'll have -1 over x cubed is less than or equal to sine of x over x cubed is less than or equal to 1 over x cubed. So we've got this function less than that function less than this function. Now if we take the limit as x approaches infinity, was it? Yeah. As x approaches infinity, oh that's good, yeah, x approaches infinity. Okay, so -1 over, plug in a big number for x, you cube a big number, you get an even bigger number. So fixed number over a big number, that's going to go to 0. Please don't write 1 over infinity. Just think about if I pick x to be big, then the y, and by y I mean -1 over x cubed, that's going to be big. So then the overall result of what's the y coordinate getting closer and closer to is going to be 0. Similarly, the limit as x approaches infinity of this other function over here, same deal. Fixed number in the numerator, a growing number in the denominator, 1 over a huge number, 1 over a huger number, is that a word? Gets closer and closer to 0. Since the limit of the outside functions here and here match, they're both 0, and we've squeezed this function on the inside by the squeeze theorem, we end up with the limit, same x approaches infinity, of this function in the middle, sine of x over x cubed, this is equal to 0 as well. The next problem in this is actually another squeeze theorem problem. Let's take a look. Part G is limit x approaches infinity arc tan x over x. Now let me just write in red a thing that sometimes people try to do to start. Is people will say arc tan of x is between 1 and -1. Trying to do what's here, right? Okay, that's true for sine. The value of sine is between -1 and 1. If you graph it, right, the sine graph does that. Arctan, though, that's not true, right? So arctan, we've got to be a little more careful. Arctan of x goes not between -1 and 1. If you graph the arctan graph, right, it goes between -π/2 and π/2. So that's where we should start. But whatever, that's a number. -π/2 is a number, π/2 is a number. It's a different number. π/2 is like approximately 1.57. So just to stick a 1 there is like, it's literally not true, right? If you had just changed these -1 and +1 to 2's, -2, +2, you'd have a true statement. Because this number is like 1.57-ish, right? Okay, we'll take this double inequality though, and we'll divide all 3 sides. Side 1, side 2, side 3. In all cases, we'll divide by x cubed again. Just to, oh yeah, sorry, I didn't even write the right problem. So -π/2 over an x cubed less than or equal to arctan of x over an x cubed. We're dividing all 3 sides, so this π/2 over there over an x cubed. Now the point is the limit as x approaches, oh yeah, infinity, that's good, of this first function, -π/2 over x cubed. Same principle as we saw here, limit of a fixed number over a growing number. Fixed number -π/2 over a growing number, right? X cubed is huge as x gets big. So this is 0. Limit of the other outside function, limit x approaches infinity of π/2 over x cubed. This is also equal to 0. So by the squeeze theorem, the limit of the middle function, the function that's been squeezed, the limit as x approaches infinity of the function in the middle is also equal to 0. What about these last 2 here? So we've got a part H and a part I. Okay, these are very similar style problems. So part H, We got limit x approaches 0 from the right of x to the x. All right, so what we'll do is, actually, let's leave out the limit for a second. Let's just look at the x to the x. Is that the right problem? Yeah, x to the x. Okay. So y is equal to x to the x. Whenever you have the variable in both the base and the exponent, you should go to this. This is the go-to. Ln both sides. Ln of y equals ln of x to the x. Why do that? Well, we can leave the left side as it is, but the right side, we can rewrite it down here by taking that x here and bringing it in front. It's just a law of logarithms that lets us write x times ln of x. Okay, now let's apply a limit to both sides. What limit? The limit as x approaches 0 from the right. So this ln of y, we'll stick in front of it, limit x approaches 0 from the right of ln of y. After the equal sign, we'll need a little bit of space because we need to take that same limit thingy. Write this here, limit x approaches 0 from the right of x times ln of x. All we literally did, I know it looks a lot bigger, we took the line above, that equation here, we just apply the limit to both sides. Now ignore this for a second. We're going to come back to this later. Let's just look at this right here. So there's two factors. There's an x, and then there's a times ln of x, not times x. Here, this is ln of x. Right? So x times ln of x. Well, as x approaches 0 from the right, x goes to 0. This factor goes to 0. This factor goes to negative infinity. Think of the graph of ln of x. Right? So what we need to do is reorganize this using some algebra. Let's write this as limit x approaches 0 from the right. We'll leave that ln of x where it was. And my temptation is to just want to take that x and stick it in the denominator, but we can't just do that. That changes the problem. So we don't do that. What we have to do so that we have something that's algebraically valid is, instead of just writing this x that was in the numerator here, we can write 1 over x there. I'm saying give it to your friend in algebra. You give your friend ln of x over 1 over x, they ought to produce for you x times ln of x. Right? So those are algebraically equal. Now if we look at this limit problem, let's see, the limit of the top is a negative infinity. The limit of the bottom, if you pick x to be just slightly bigger than 0, then like 0.1, right? Then 1 over 0.1, okay, 10, 1 over 0.01, 100. So the bottom is also, by bottom I mean 1 over x. That's going to infinity. So we've got an infinity over infinity L'Hopital's form, and that means we can do the following. Limit x approaches 0 from the right. The derivative of ln of x, we put here 1 over x. We differentiate the bottom separately and have negative 1 over x squared. Now let's reorganize. So limit x approaches 0 from the right. We can multiply by the reciprocal of the denominator. So 1 over x was in the numerator times negative x squared over 1. The negative could be down there, right? You get a cancellation. So limit x approaches 0 from the right. I believe just negative x, because you cancel an x on top and bottom. There's otherwise one remaining factor of x in the numerator and a minus sign floating around. Here we can apply DSP. Yeah, it's a one-sided limit, but this is a polynomial. So the one-sided limits are going to agree to whatever the two-sided limit value is. So we get negative 0 here, which is 0. We're not done. Here's this thing that we didn't consider. It said later. So if we take this entire line of work, so it's kind of curved like this, we can say, as a summary, limit x approaches 0 from the right of ln of y is equal to this thing, this 0. Now let's swap these two. So ln's a continuous function. We can actually swap the order of these and have ln first, the limit part written next. And then that y we'll copy down here, equals 0. Using the definition of logarithm, this can become this part, the input to the logarithm. So limit x approaches 0 from the right of y equals the base here, e to the 0. We'll simplify the right side. E to the 0 is 1. And for the left side, let's just rewrite this. Limit x approaches 0 from the right. What was y? Well, it was up here. It was x to the x. And take a look. That was the original question right there. Okay, so it wasn't immediately a L'Hopital problem. It was do some algebra, especially with this ln. It allows us to take this awkward situation of x to the x and not have the variable in the base and the exponent by using a log law. And eventually over here we saw a L'Hopital. Okay, we have one last limit problem here in this list. Let's do that. So, part I. Limit x approaches infinity of x to the 1 over x power. Okay, so what we'll do, same deal, right? So the variable appears in both the base, in the x, and in the exponent, 1 over x. I said x, right? So what we'll do is do a y equals x to the 1 over x again. Ln both sides. X to the 1 over x. All this was done so that we could take that 1 over x and bring it in front of this ln. So the ln of y equals 1 over x times ln of x. Now, like over here, we'll take a limit on both sides. This time it's a limit as x approaches infinity. Right? So limit x approaches infinity of ln of y equals limit x approaches infinity of this. But let's reorganize this as ln of x over just an x. Okay, that works here, right? This is already a 1 over x in front, so we can just write it next to the denominator. Here, it'll work a little harder. That x we wrote as a 1 over x in the denominator. Okay, so then here, this is a L'Hopital's form, because if x gets big, ln of x gets big, and if x gets big, x gets big. So this is an infinity over infinity. Both the top and bottom grow as x gets big. So then we'll have a new limit problem. Limit x approaches infinity of, well, ln of x differentiates to 1 over x. And x differentiates to 1. So we'll limit x approaches infinity. Just cleaning this up by not writing the over 1. We'll just have this 1 over x copied down there. Now let's think about this, right? Limit as x approaches infinity of the following thing. The y value, not that y, but this our new y, right? So this function 1 over x. Think about what happens to 1 over x. So 1 over a growing number, right? X gets big. So 1 over 10, 1 over 100, 1 over a million, 1 over a billion. This gets closer and closer to 0. Oh yeah, and then just like before, we've got to like take this, set it equal to that, right? We haven't really dealt with this part yet. So let's take limit x approaches infinity ln of y. So that, say, we've said that that actually is going to equal 0. Swap here, ln first, limit next. We can get the y after. We could literally write just the symbol y, but we could also just write x to the 1 over x here and have 0. And then apply the definition of logarithm to have the input to the logarithm. And this was the input to that natural logarithm, is equal to the base of the logarithm raised to the this, which e to the 0 simplifies.